Welcome, everyone. In today's session, we are going to explore the essential skills of reading, writing, and downloading data using Python. Being able to manage data effectively is a cornerstone of almost any programming task, especially in scientific computing and data analysis. Our main goal is to equip you with the practical knowledge to interact with data files, whether they are stored locally or need to be fetched from the internet. We will start by learning how to download a file from a given web address and save it onto your computer. Then we will dive into various methods for reading data from files into our Python environment, and conversely, how to write data from our programs back into files. We will cover different file types and the Python tools best suited for each, including the requests library for web access, NumPy for numerical data, and Python's built-in functions for general file operations. Understanding these techniques will allow you to handle datasets for your projects, analyze experimental results, and share your findings. This lesson is structured to progressively build your skills, starting with basic download and save operations, moving through reading and inspecting data, and finally exploring different ways to export your processed data. First, let us look at how we can retrieve a data file from an online source. The code block begins by importing necessary libraries: requests for handling web requests, NumPy for numerical operations later on, and matplotlib for plotting, though we are not using all of them immediately. We define a variable, URL, that holds the web address of the data file we want to download. The requests.get function is then called with this URL, which performs the action of fetching the file from the internet. The result of this download, which includes the file's content and other information, is stored in an object named downloadbj. Following that, we use Python's built-in open function to create a new file named boltzmann.date on our local disk in write binary mode, indicated by WB. The with statement ensures the file is properly closed after we are done. Inside this block, write is used to take the actual content of the downloaded file, accessed via downloadobj.content, and write it into our newly created boltzmann.dat file. The suffix dat is often used for data files, but, as noted, the specific suffix is not critically important for how the data is handled programmatically. After attempting to download and save the file, it is good practice to verify that the file was indeed created in the expected location. This code snippet uses the os module, which provides functions for interacting with the operating system. First, os-get-cwd prints the current working directory, so we know where Python is looking for files. Then, os-listdir is used to list the contents of the current directory. We are displaying only the first 20 items for brevity. Finally, ospath.icefile, followed by our file name, boltzmann.dat. Check specifically for the existence of this file, and will return true if it is found, or false otherwise. This confirmation step is crucial before we proceed to read and process the file, ensuring that our data source is actually available. Now that we have confirmed our data file boltzmann.date exists, we can proceed to read its contents into our Python environment. For files that contain purely numerical data, like the one we are using, the NumPy library offers a very convenient function called loadtxt. This function is designed to read data from a text file and interpret it as an array of numbers. The code imports NumPy again, although it was imported earlier, which is redundant but harmless. The core action is data equals NumPy dot load txt with the file name boltzmann.date as an argument. This command reads the entire file, assumes the data is organized in rows and columns of numbers, and stores it into a NumPy array named data. It is important to remember that numpy.load txt works best when the file does not contain non-numeric text or headers, unless specific options are used to handle them. Once the data is loaded into the NumPy array, the next step is often to inspect its structure and type. This helps us understand what we are working with. The code uses two print statements for this purpose. The first one, print type data, will show us the type of the data object itself. Since we used numpy.load.txt, we expect this to be a numpy-nd array, which is NumPy's fundamental array type. The second statement, print numpy.shape data, reveals the dimensions of the array. For a two-dimensional dataset, this will typically return a tuple indicating the number of rows and the number of columns. In this specific case, we are told it has 421 rows and 2 columns, confirming it is a two-dimensional array ready for further manipulation or analysis. With our data loaded into a two-dimensional NumPy array, we can explore how to access specific parts of it using a technique called slicing. The first example, data, followed by square brackets containing 1:30 feet, selects rows starting from index 1 up to, but not including, index 3, and specifically from the column at index 0, which is the first column. The next example, data, with 1:3, in the brackets, again selects rows 1 and 2, but the colon by itself for the second dimension means it selects all columns for these rows. Finally, data, with :10, in the brackets, indicates selection of all rows from the beginning up to, but not including, row index 10, and again, all columns. Slicing is a powerful way to extract subsets of your data for focused analysis or processing. Let us continue with a few more examples of slicing to solidify our understanding. The expression data with :10 feet in brackets will extract the first 10 rows, similar to the previous example, but only from the first column, which is column index 0. Similarly, data with :10 1 foot in brackets will get the first 10 rows from the second column, which is column index 1. After these slicing examples, the code print data 0 displays the entire first row of the array. Then, print data 00 accesses and prints the element at the very beginning of the array, that is, the element in the first row and first column. Finally, print type data 00 checks and displays the data type of this individual element. This is useful to confirm that numpy.load.txt has correctly interpreted the file's content as numerical values, typically floating point numbers in such cases. After loading and inspecting our data, a common and insightful next step is to visualize it. This code snippet demonstrates how to create a simple scatter plot from our two-dimensional data array. First, we import the PyPlot module from the matplotlib library, which is a very popular plotting tool in Python, and we give it the alias plt. We then create two new arrays, zar and yar. The array zar is formed by taking all rows, indicated by the colon, from the first column, index 0, of our data array. Similarly, yar is formed by taking all rows from the second column, index 1, of the data array. With these two arrays representing our x and y coordinates, we use plt_scatter, sar, yar, to generate a scatter plot. This will display each pair of x-y values as a point, giving us a visual representation of the relationship between the two variables in our dataset. Now, let us consider how to save our numerical data, which is currently in a NumPy array, back into an external file. The NumPy library provides a convenient function called save_txt for this purpose. The code snippet shows how to use it. We use the withopen statement to open a file named npsave_txt.csv in write mode, indicated by W. The CSV's suffix suggests we are saving it in a comma-separated value format, which is a common text-based format for tabular data. Inside the with block, numpy.save txt is called. The first argument is the file object f, and the second argument is our NumPy array data. This function will write the contents of the data array into the specified file, typically with values in each row separated by spaces or tabs by default, or commas if specified. After saving our data to the file npsavetxt.csvs using numpy.savetxt, it is a good idea to verify that we can read it back correctly. This code block demonstrates how to do just that. We re-import NumPy. Then, we use numpy.loadtxt, the same function we used earlier, to read the data from npsavetxt.csv and store it into a new array called numData. To check the contents and data types, the code then iterates through the first 10 rows of numData using a for loop. For each row I, it prints the row itself, and then it prints the type of the first element, I, and the type of the second element, I. This helps confirm that the data has been read back as numerical types, just as it was before saving. Let us explore another way to write numerical data to a file, this time using Python's fundamental file input-output operations. The code first reloads the numerical data from npsavetxt.csvs into the numData array using numpy.loadtxt. Then, it opens a new file named sampleout.csv in write mode using f=open sampleout.csv. The core of this snippet is a for loop that iterates through each row E in the numData array. Inside the loop, fwrite is used to write data to the file. A crucial point here is that fwrite only accepts strings. Therefore, each numerical element, is0 and, must be converted to a string using str before writing. These string representations are concatenated with a space in between, and a new line character, \n, is added at the end to ensure each row from numData appears on a new line in the output file. Finally, fclose is called to ensure the file is properly closed and all data is written to disk. Now, let us see if the file sampleout.csv, which we created by manually writing strings of numbers, can be read back using numpy.loadtxt. This code block attempts to do just that. It imports numpy and then calls numpy.loadtxt sampleout.csv, storing the result in an array named sampleout.csv. Similar to a previous check, it then iterates through the first 10 rows of this newly loaded array. For each row I, it prints the row and the data types of its first and second elements. If numpy.loadtxt can successfully parse the file, it means our manual string formatting in the previous step was compatible with what loadtxt expects, which is typically space or comma separated numerical values. This demonstrates the robustness of loadtxt when dealing with simple text files containing numbers. We will now explore a different method for reading file content using Python's built-in readlines function. Unlike numpy.loadtxt, which tries to interpret data numerically, readlines treats everything as text. The code opens the file sampleout.csv in read mode R. Then, raw data equals freadlines, reads all lines from the file and stores them as a list of strings in the variable raw data. Each element in this list corresponds to one line from the file, including any new line characters at the end of the lines. The for loop then iterates through the first 5 lines of raw data. For each line E, it prints the line itself and its type, using type I. This will confirm that each item read by readlines is indeed a string. Finally, fclose closes the file. When data is read using freadlines, each line is a string. If this string represents numerical data that we want to use in calculations, we need to convert it. This code block shows how to do that. It opens sampleout.csv and reads its lines into raw data. Then, it iterates through each string I in raw data. For each line, iStrip is called to remove leading or trailing whitespace, such as the new line character. After stripping, iSplit splits the string into a list of substrings using a space as the delimiter. Assuming each line has two numbers separated by a space, this results in a list of two string elements. These string elements, iSplit 0 and iSplit 1, are then converted to floating point numbers using float and assigned to variables x and y. This process of stripping, splitting, and converting is a common pattern when parsing numerical data read as plain text. Let us now consider how to write a list of strings to a file. This is useful when you have textual data, not necessarily numerical, that you want to save. The code first uses OSListDir to get a list of all files and directories in the current working directory and stores this list in the variable data. It prints the first 10 items of this list to show what kind of string data we are dealing with. Then, it opens a new file named strings.csv in write mode. A for loop iterates through the first 10 strings I in the data list. Inside the loop, each string I is printed to the console, and then fwrite I plus n writes the string I, followed by a new line character to the file, strings.csv. This ensures each file name appears on a separate line in the output file. Finally, fclose closes the file. Having written a list of strings to the file strings.csv, we can now see how to read it back using freadlines. The code uses a withOpen statement to open strings.csv in read mode R. This is a good practice as it ensures the file is automatically closed. The command rawdata equals freadlines reads all lines from the file into a list of strings called raw data. Then, a for loop iterates through each string E in this raw data list. Inside the loop, print.strip is used. The strip method is important here because readlines includes the new line character at the end of each line read from the file. Using strip removes this, along with any other leading or trailing whitespace, giving us cleaner strings when printed. Let us briefly summarize the file input and output techniques we have covered so far. We have seen how to export data to an external file using numpy.savetxt, which is particularly useful for NumPy arrays containing numerical data. Correspondingly, we learned to read numerical data from an external file using numpy.loadtxt. We also explored more general methods for file handling, exporting data to an external file using the basic f.write method, which requires converting data to strings first, and reading data from an external file using f.readlines, which reads data line by line as strings. These methods form the foundational tools for data persistence in Python. Beyond basic file operations and NumPy-specific functions, Python offers specialized modules for handling structured data formats like CSV, which stands for comma-separated values. The CSVs module provides tools such as CSV Reader and CSV Writer to work with such files. In this code example, we first import the CSV module. We then open our previously created strings.csvs file in read mode. A CSV Reader object is created from this file object, which allows us to iterate over rows in the CSV file, treating commas as delimiters. Nested within this, we open another file, strings2.csv, in write mode. A CSV Writer object is created for this output file. The command writer.writeRows raw data, then takes all the rows read by CSV Reader and writes them into strings2.csv, effectively copying the content while properly handling CSV formatting. The new line equals argument in open for writing is often recommended when working with CSV files to prevent blank rows. The CSV module's writer can also be used to save numerical data that you might have in a NumPy array. This code snippet demonstrates such a scenario. First, it loads numerical data from the npsave.txt.csv file into a NumPy array called raw data, using numpy.loadtxt. This raw data array now holds our numbers in a structured way. Then, it opens a new file named numdata.csv in write mode, again using newline equals for good practice with CSV files. A CSV writer object is created, associated with this output file. Finally, writer.writeRows raw data is called. Since raw data is a NumPy array, which is an iterable of rows, where each row is an iterable of items, writeRows will iterate through it and write each row to the numdata.csv file, with elements in each row separated by commas by default. This shows how you can easily export NumPy array data into a standard CSV format. This example further illustrates using the CSVs module, this time for both reading and writing data that is originally in a CSV text file format, like our npsavetxt.csv. We open npsavetxt.csv in read mode. A CSV Reader object named raw data is created from it. This raw data object will yield rows from the input CSV, where each row is a list of strings. Then, we open a new file, numdata2.csv, in write mode and create a CSV Writer object for it. The writer.writeRows raw data command then takes the rows, which are lists of strings, provided by the CSV Reader, and writes them into numdata2.csv. This effectively copies the CSV file. It is important to note that CSV Reader reads all fields as strings. If numerical interpretation is needed later, conversion would be required, unless a library like Pandas is used for reading. We now introduce Pandas, a very powerful library in Python for data manipulation and analysis, which also offers robust capabilities for reading and writing data in various formats, including CSV files. The primary data structure in Pandas is the data frame. This code first loads numerical data from npsavetxt.csv into a NumPy array named raw data. Then, this NumPy array is used to create a Pandas data frame called df. Writing this data frame to a CSV file is straightforward. df.to_csv pd_sample.csv saves the data frame, including an index by default. Reading data back is equally simple. df2 equals pd read_csv pd_sample.csv loads the CSV file into a new data frame, df2. The code then demonstrates accessing columns from df2 feet using iloc for integer location-based indexing to extract data for x and y variables, which are subsequently used to create a scatter plot with matplotlib, showcasing a typical workflow. In wrapping up our exploration of reading and writing data, it is clear that Python offers a spectrum of tools, each with its own strengths. We started with fundamental file operations like f.write and f.readlines, which provide fine-grained control but require manual handling of data types, such as converting strings to numbers. We then saw how numpy.loadtxt and numpy.savetxt are optimized for numerical data stored in text files. The CSV module, with its reader and writer objects, offers a more structured approach to handling comma-separated value files, simplifying the parsing and generation of CSV-formatted text. Finally, we touched upon Pandas, which provides high-level functions like read_CSV and to_CSV. These Pandas functions, much like the CSV's module tools, offer significant convenience by often automatically handling data type conversions and managing file structures, making data input and output operations more efficient and less error-prone, especially for complex datasets. Choosing the right tool depends on the nature of your data and the complexity of your task.